absolute and conditional convergence. Okay, so now, so far we've been dealing with positive sequences in that the terms are always greater than 0, right? But now we're going to devise a way, or other people have devised a way for us, and we're going to learn that, to deal with both positive and negative sequences. So positive and negative sequences, okay? So the first, I'd like to define a couple of terms. So it's termed absolute convergence. I'm going to abbreviate. So CONV is convergence. Absolute convergence is when the absolute value of a sequence converges. So it's kind of standard and like straightforward. You can just tell in the name. Absolute convergence means that the absolute value of a sequence converges. Okay, so that's the first definition. And the second definition is conditional convergence. So conditional convergence. So this, on the other hand, is when the sequence itself converges, that's a V, but the absolute value of it, the absolute value, diverges, okay? And then along with that, the absolute value, the absolute convergence, there is a theorem, and the theorem basically just states that absolute convergence implies convergence. So that one's kind of like redundant, but I'll write it here anyways, just for your reference. So it says if the absolute value of a sequence converges, then the sequence itself, without the absolute value sign, will converge. Okay? Converges as well. Okay, so that's the theorem to go along with absolute convergence. Okay, now I'm going to explain what do all of these kinds of convergences mean. So basically, the way that I learned this initially in a previous math class of mine is, let's say we start at 0 here, and our first A1, our first term goes like this, okay? So this is going to be in the case where AN, we're taking the absolute value of AN, okay? So it doesn't matter if A1 is positive or if A2 is negative or anything like that. We're taking the absolute value, so that means we're going to be adding the positive values of everything, okay? So let's say this is length A1, or this is the A1 value, so this point would be our S1, our first partial sums, okay? And then on top of that, we're going to add A2, and we have to add the positive value because we're taking absolute value, or we're going to take the positive value of A2, no matter what its sign is, because we're dealing with the absolute value of the sequence. Okay, so this A2 has to be to the right, and then, so if we add A1 plus A2, here is our S2 value, our second partial sums, okay? And then let's say we have another A3 and so on. Okay, so here would be our S3 and so on and so forth, okay? So basically, what this means is that when we're taking the infinite sums of the absolute value of a sequence, this is what we're doing, is adding the positive values of each successive term to the end to come up with the partial sums, okay? And then this just means as n goes to infinity kind of thing. So this is going to end up being your infinite sum somewhere over here. And you see how the way I've depicted this is A1 is pretty large, and then A2 is smaller than A1, and A3 is smaller than A2. And I did that for a reason, to show that for this absolute value of the sequence to converge upon a certain number, it has to be doing this. Each succeeding term has to be less in magnitude than the previous one. Because if you think about it, let's here, we have another number line. Here's 0, and let's say this is A1, okay? So this is our length A1. If A2 is greater than that, then that means you're going to be adding more and more and more and just continue on to infinity, okay? So basically, I'm going to go over this again. I'll write out here, if the terms, if the magnitude of the terms, if terms magnitude decreases, DEC, fast enough, then this will be true. Then this part, this infinite sums will converge. So this will converge. Okay. Whereas this case, this example down here, this would not converge. Okay. But there's no real like notation for this. I was just showing an example. So this probably wouldn't converge. Okay. Now on the next slide, I'll show you a different dynamic. So now let's say this is what I'm going to introduce what's called an alternating series. Alternating series. Okay. So what this is what it looks like mathematically. So we have our infinite sums as n goes from 1 to infinity, or from any number really. And then we have our an, like normal, but no absolute value here. And in front we have a -1 raised to the n power, or some n power. Or it could be n, it could be n minus 1, depending on the sequence. But this is basically going to look like a1, some term here. And then this -1, this factor in front, that's going to alternate, hence the alternating part here, alternate the sign in front of each term. So then we have a plus, minus, a plus, a3, minus, a4, plus, and etc. All the way on to the infinity term. Or basically, here's some conditions where terms, so each value itself, disregarding the negative and the positives in front, each term has to be decreasing, are positive and decreasing. And decreasing in this sense, as I said before, in the other number line, our A1, let's say it's this long, our A2 has to be shorter than that. Okay, well, that was a weird line. That's A2, and then A3 has to be smaller than A2 in order for this to hold true. So, yeah, okay. So from there, then we could say, well, now I'll depict what's going on here. Okay. This is what this is going to look like on a number line. So let's say we have our line. Hey, that was a pretty good line. Let's say our 0 is here. Okay. So we're starting here. And let's say A1 it's some positive number, right? Because it's the first positive term. Let's say it's this long. Okay. I'm just doing this for exaggeration. But so this is A1, okay? So our first partial sums will be right here, right? Because it's only the A1 term. And then when we do S sub 2, the second partial sums, we're going to take the sum of A1 minus A2. And as we know, A2 in magnitude has to be smaller than A1. But here, this negative sign, that means it's going in the opposite direction. So A2 is going to go from here all the way to somewhere shorter than A1, right? So this is like our minus A2. So that brings us back almost to the start. Or it could end here, it could end anywhere, it just can't go past 0 again, okay? So here's our S sub 2. And now let's look at the third partial sum. So that now we're including the plus A3. So we're up to this point here, and then we're going to add the third term, okay, which has to be shorter than the length of the A2 factor here. So this is A3, okay, positive A3, and then we have our third partial sums, and it's just going to keep going back and forth. So if we do the fourth term, for example, here's A4, and this is going to be a minus, right, because we're alternating. This is a minus whoa, that was a weird 4, A4. And then we're going to have, that didn't line up either. So S sub 4 is here, and then we're just going to keep going back and forth and back and forth. And you see how eventually we'll close in on some number. and keep getting closer and closer. Okay? So this point, or wherever it is in between here, that's going to end up being our infinite sums. Okay? So in effect, the this term in front here, this factor of -1 to the n, or to the n minus 1, whatever that is, it kind of helps the series converge, right? Because you're not really, like in the previous slide, how we had to keep adding positive terms, so that kept bringing us more and more to the right, correct? So this helps series converge in the sense that this is kind of like go forward a step and then back a little bit, go forward a little bit and then go back a little bit. So this is kind of like what's called an oscillating motion, but not quite. It becomes less and less until it converges on this one infinite sum. Okay, so now we're going to go over a test for this alternating series.